All right, guys, let's go ahead and get started. I have some stuff definitely we can go over in the next chapter. First, though, I want to give you guys any opportunities to ask any questions about the material on the exam, if you would like. So basically what we're going to do is we're going to do the first part of the class is sort of a Q&A review, if you have anything, and then we'll use the remaining time for other stuff. So now, obviously, the goal becomes let's find as many questions as we can so he doesn't get into any more new stuff today. I'm guessing, right? Yep. We'll see how that goes. Josh, did you have a question?
We'll just go over like how to determine whether something is conjugated, whether it be a string or a regular carbon chain, especially when they're positive.
So how to determine whether something's conjugated or whether something's aromatic? Conjugated? Okay. Yeah. How do you determine whether something's conjugated? Well, at the heart, there is a definition of conjugation that you always have to keep in mind. What does it mean to be conjugated? You have to have at least 3 consecutive atoms with an available p orbital, right? And that will correspond to sp2 or sp. It can be sp hybridized as well. All right. So, one of the primary examples that we looked at was conjugated dienes. Right. So we saw something like this. Right. We look at the hybridization of all of these. That's going to have sp3 hybridization. That one's going to be sp2, 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 sp3. Okay? So, if we're looking for available p orbitals, right, we said it's got to be either sp2 or sp hybridized. Well, we have 4 of them right over here in a row that have this, right? And the definition is that you got to have at least 3, right? So, because you have all these guys that can overlap, this meets our definition of a conjugated compound. Yep. Now, just because it's a diene doesn't mean necessarily that it's conjugated diene. This one is non-conjugated. Why is this one not conjugated, whereas the top one is? Yeah. Sorry, I couldn't hear you.
There's only 2 consecutive.
Yeah. At no point in here do you have 2 consecutive overlapping p orbitals. This one's sp2. This one's sp2. So you have extra p orbitals there and there. Same thing for these guys, but you have these sp3 orbitals, or hybridized carbons, in the middle, right? So at no point do you ever actually have 3 in a row. So that one's non-conjugated. All right? That's how you can tell with dienes whether you have a conjugated system or not. We learned of another really common conjugated system. Y'all remember what it was? In that chapter, conjugated dienes. There was another really common one we learned about. Let you guys look it up. What's that? No, further back, towards the beginning of that chapter. Bless you. when we were first learning what it meant to be a conjugated species. There were two main ones that I introduced in that chapter. One was conjugated dienes. I'm gonna feel really stupid if I ended up not mentioning it, but I'm pretty sure I did.
The allele carbocations?
Whoa, we have a Zoom participant. Somebody got tired of waiting. Yes, the allele carbocation. Very good. Y'all remember this? Yeah. Allelic carbocation, right? This is one that you can see, well, these two carbons are obviously sp2 hybridized. Hopefully you can tell that by now. So they have available p orbitals. This carbon, since it's positively charged, it's only got 6 electrons. This means it's only got 2 H's off of it. That has 3 groups on it. So that means it's sp2 hybridized. Right? So we have another situation where we can have overlap of 3 consecutive p orbitals. So yeah, anytime you have an allelic carbocation, that is a conjugated system. Again, you have to be careful though. Is this a conjugated system? Why not? Mm-hmm. You have this extra carbon right over here, right? This is not an allelic carbocation. It just happens to be a molecule or a species that has a carbon-carbon double bond and a positive carbon. But this is not in the allele position. So that would not be conjugated. Excuse me. Does that make sense? There's some other situations that we didn't go over that could qualify, though, as conjugated. We didn't really look at sp hybridized carbons. But theoretically, yeah, they can be involved in conjugated systems. This one's conjugated. We have a positive carbon next to, directly adjacent to carbon-carbon triple bond. Each of these has 2 p orbitals. This one has 1. They can all overlap. Conjugated system. Allyl carbanion. That can also be conjugated. Why? This is a tricky one. How come this one's conjugated?
Doesn't it have to do with resonance?
It does have to do with resonance. Yeah. Right? Again, with conjugation, it's all about figuring out, does your atom have an available p orbital for overlap, right? Normally, it looks like this carbon would be sp3 hybridized, right? But you guys remember partial double bond character? Yeah. You can draw a resonance structure for that one. And in this case, this carbon would be sp2 hybridized. So allyl carbanions are conjugated systems as well. Yeah.
part of the SP2 hybridized just because you switched it, so it has the possibility of being.
Yeah, basically, when you have something like this, all right, just looking at it in this state, it looks like it should be SP3 hybridized according to the rules that we learned in chapter 1, right? But basically, you have to remember, this doesn't really exist. This doesn't really exist. The true structure is somewhere in between, right? So to even accommodate a partial double bond, like it does in its true state, it has to have that sp2 hybridization. Otherwise, it could not even do this. It could only exist in that state. Okay, so that's why it actually has the sp2 and not the sp3 hybridization. Excuse me. My voice is a little bit better today, but still not fully there. Josh, did that help answer your question? Aromatic rings with different atoms. Sure. Wish I'd brought my book today. It's okay, I can come up with some examples off the top. All right, let's see. Here's one. Try that one. That one's got a couple of heteroatoms. All right, we're going to try to figure out whether it's aromatic, anti, or not. Okay, so yeah, you're going to have some of these on the exam. I mean, that's pretty obvious. And to figure out what they are, you have to go through the criteria list, just like we've learned in the past. Now, honestly, it's pretty easy to see this as a ring. And I'm going to tell you whether they're planar or not. So I can tell you this, I'll just say this is planar. Right. The two big things that you've really got to look out for are whether you have completely conjugated system in the ring and whether you satisfy the Huckel number of electrons for either aromatic or anti. All right. So, yes, ma'am.
In order to be aromatic, the extra electron have to be inside the ring.
Yeah, so whenever you, for aromaticity, what you do is you count up the number of pi electrons inside the ring, right? Sometimes they're easy to identify, like it's pretty easy to say that these two pairs are inside the ring. When you have heteroatoms and or charged atoms, a lot of times you have extra unshared electron pairs. They're kind of funny because they could go either inside of the ring or outside of the ring. It just depends on basically what slots are available for it, right? So that's part of our process, is trying to figure out exactly where we're going to put those. I always start by default just kind of drawing them on the outside. And then, if it turns out they actually go on the inside, I'll redraw them, put them back. Excuse me. All right, so let me ask you, what is your approach to this one? All right, you're setting out to solve this problem. What are you going to do first? That is an excellent question. Let's look at the hybridization of the atoms in the ring. All right, well, first of all, let's take care of the carbon ones. Carbons are pretty simple here, right? Is it safe to say they're all sp2 hybridized? Yeah, you guys can tell that by now, right? All right, the trickier part is the heteroatoms, all right? So let's start with nitrogen, all right? What do you think the hybridization of that nitrogen is? It is sp2 hybridized. It's got 2 bonded carbons and 1 unshared pair, so it's got 3 groups around it. So according to our classical definition, that's sp2 hybridized. Since it's sp2 hybridized, that means it's actually got 3 hybrid orbitals, and it's got 1 p orbital left over. So we'll just write that down. All right. What about this oxygen up here? sp3? Well, let's look at it. It's got 2 bonded carbon atoms, right? And it's got 2 unshared pair. That's 4 groups, so that does correspond to our classically defined sp3 hybridization. However, we learned this as an exception to that rule. Why is this an exception to the rule? This one would actually not be sp3, it would be sp2. Why is that one sp2 hybridized? What's that? It's in an allele position, right? And just like we've seen with some other species that have unshared pairs of electrons, allele, don't forget, this one can undergo resonance. Right? A pair of electrons, for example, could swoop down from oxygen to this carbon and form a double bond. And there's several resonance structures you can draw. I'm not going to draw all of them. I'll just draw one representative one here. So you can see in this case, just like we saw with one of the examples I put up a second ago, oxygen actually has partial double bond character. So for that reason, it's got to have sp2 hybridization. Does that make sense? Any questions about how we figured that out? Bottom line, if you have something with unshared pairs of electrons, and this could be a heteroatom, it could be a charged carbon, whatever. If you have something with unshared electron pairs in an allele position, you're going to be able to draw resonance structures like this. So that's going to be something you're probably going to want to be able to recognize. All right. Excuse me. All right, so we got that going. So all of these atoms in the ring are completely conjugated. So that's another check mark off our list. Now we got to see how many pi electrons we have, right? That means we got to figure out whether these electrons and these electrons go on the inside or the outside of the ring. All right, so let's do the nitrogen one first. All right. How many hybrid orbitals are being used up already on your nitrogen? I don't know if I'd say 3. What goes in hybrid orbitals? What type of electrons? Sigma. So how many sigma bonds does this nitrogen currently have? It's got 2 sigma bonds, one here, and then half the double bond, right? So 2 of those are taken up. You got 1 left. All right, now let's check the p orbitals. What type of electrons go in p orbitals? Pi. How many pi bonds does this nitrogen have? 1, right? Goodbye p orbital. So where do the electrons have to go? Yeah, they have to go in your hybrid orbital, which means they're going to be on the outside of the ring. Only the pi excuse me, only the p orbital electrons go inside the ring. All right. Same type of analysis with oxygen. How many hybrid orbitals are currently occupied? 2, sigma bond, sigma bond. How many p orbitals are currently occupied? None, because it doesn't have any pi bonds, right? So you have 2 open orbitals, you have 2 unshared pairs. That means one of them stays on the outside in the hybrid orbital. The other one goes to the inside in the p orbital. Okay? Does that make sense? Any questions about how we got this far? All right. Now the last thing you do is your Huckel calculation. How many total pi electrons do we have now? We have 6. 2, 4, 6. All right, if we try the aromatic formula, 4n plus 2 equals 6. Remember, n has to be a whole number. If you do some algebra, you'll see that n equals 1. So yes, this is an aromatic compound. Just a heads up, if n equals 0 works, then it also qualifies. So 0 counts as a whole number for this purposes. Okay? Does that make sense? Now, don't be fooled. I could have a pretty similar looking compound here that could be totally different. This is very similar, but not quite the same. What can you tell me about this one? Sarah? It's not completely conjugated. You got this little guy right over here. This sp3 hybridized. So that violates one of your first 3 criteria. What does that mean? It's non-aromatic. Yeah. So be sure to have a sharp eye, pay close attention to detail whenever you're looking at these. How small details can make a big difference. Excuse me. Yeah.
Referring back to the double partial double bond character,
Mm-hmm.
you do that four carbon chain. Would it change anything if it was just 2 lone? If it was just a lone pair of electrons without a negative charge? Does that change the configuration?
Tell me what you draw.
So 4 carbon chain and then double bond between 3 and 4, and then negative on 2.
Here. Negative over here.
So
Without the electrons?
yeah. Okay.
That is impossible. Yeah. The only way this carbon will go negative is if it has an extra unshared pair of electrons. Yeah, if there's no electrons here, then there's only 2 possibilities. You would either have this, in which it would actually be deficient of electrons, right, 2, 4, 6, and it would have a positive charge, or it would just exist as having 2 H's. Right, so the what you're describing actually is not possible. Radical addition? Yeah, radical addition to a double bond mechanism. We can do that. Let's see. All right, first thing to recognize here is recognize when you're actually going to have a radical addition to a double bond, right? You have to be able to recognize conditions. You can have an alkene, and you can add HBr to it. That's actually an old reaction. We learned about that in whatever the alkenes chapter was, right? Just going to give you, Sarah, I'm kind of going back to give you a broader picture, so bear with me, I'll get to the point in a minute. If we go to the alkenes chapter, if you'll remember, this actually was not a radical mechanism. This is an ionic mechanism. Do y'all remember what the first step of that mechanism was? See how much you remember. Give you practice for the final exam. What's that? Yeah, hydrogen would attach itself to one of these carbons using pi electrons. Now, which carbon would it attach to? And how did you know that? Was it a certain rule by chance? Markovnikov's rule, yeah. Created the carbocation right there. Br minus comes in. Boom, you get a product. Okay? That's an ionic hydrohalogenation of a double bond. And when you do this, it gives you Markovnikov product. So this is classified as a Markovnikov addition. All right? That's important background because why the heck do you do a radical addition instead of an ionic addition to a double bond? Well, you do a radical addition when you want an anti-Markovnikov addition. All right, so let's say you didn't want to put that Br in that spot. You wanted to put the Br at the very end, right? That's anti-Markovnikov. That proceeds by a different mechanism. So you use HBr, but you also add other things to it. You add a peroxide, and you add some sort of energy source. We'll just use heat. All right? And by adding those items, you assure this does not go ionically. You assure that this goes radical. Right? So that's one big thing, being able to recognize the conditions to tell you whether it's going to go ionic or radical. Now, as far as the actual mechanism goes, well, any radical mechanism has 3 stages, right? What's the first one? Initiation. All right, your goal in initiation is to produce your halogen radical. And in this particular case, that actually requires 2 steps, 2 initiation steps. All right, first part of this is that your peroxide is going to break apart. All right, peroxides have very weak OO single bonds. So whenever heat is applied, that peroxide is going to break up. You're going to end up with a couple of initiator radicals. And then one of those initiator radicals is going to help you get your bromine radical. How's it going to do that? What's your initiator radical going to interact with? HBr, right? What's it going to do to HBr? It's going to grab a hydrogen radical, right? And that produces an alcohol, which we don't care about anymore. And it produces the bromine radical, which we do care about very much. Excuse me. Okay, so far so good. All right, I'm gonna erase this button. All right, so we've accomplished our goal of getting a bromine radical. Then we move on to the second stage, that's propagation. That is where your bromine radical is going to interact with your hydrocarbon. All right? So basically what the bromine radical does is it breaks apart the pi bond and it uses one of those electrons to attach itself to one of the carbons. You have two different possibilities in this case. You could do this, where the Br radical would attach itself with this electron over here, and then leave a radical on that carbon. Or you could go the other way. Attach it on the very end and leave a radical on that carbon. Those are your two possibilities. They're not both going to happen though. Not in this case. Which one are we actually going to form? The one on the left or the one on the right? Why the one on the right? More stable radical. That's a secondary radical. This is a primary, right? Secondary is better than primary. So remember, bromination is selective. That is why we get this anti-Markovnikov addition, because of the need to make a more stable radical species. And then this guy can interact with another HBr. You can grab a proton, or excuse me, grab an H radical there to complete your product. And you produce more Br radical to keep the process going. Termination? Yeah, termination, you know, for your purposes in all these, terminations are basically just combinations of radicals. And, you know, depending on you know, what species you have in there, you can have different things. What were you asking about the bromine?
With the bromine radical attached to the radical.
Yeah, that's another way you can form product from this, certainly. Oh, wait. Oh, I think I see what you're saying. So you're wondering if this would happen? Yeah. A little bit, not very much. Probably just trace amounts of it. But yeah, it is possible for that to form in a little bit, in small amounts. And that's something to realize anytime you do an organic reaction, and you know, you guys have done like three syntheses in lab, so maybe you're kind of getting the feel for this, but it's nice to think that you're going to set all this up and you get like this one clean little product. But the reality is, whenever you make an organic material, you usually have side reactions, side products and stuff that are there. That's why we go through that purification.
How many reactions do we need to do stuff? Because we need to do like VR.
Like if I ask you to do the mechanism, like what do you want? What do I want from you? Is that what you're asking?
Yeah, what do you,
Just put, for terminations, I'm not too worried about it. Just put like, you could just write combination of radicals. And that would be fine. With one exception, and that is in the allylic bromination reaction. There is one particular very important termination that occurs in the allylic bromination, right? That's where you form Br2 from 2 bromine radicals. And that Br2 gets cycled back into propagation. But other than that, I'm not too concerned about any. I'm more concerned about initiation propagation in most cases.
we would not want to write that. Where it recycles back in propagation.
You'll want to include that one because that one's important. Because without that Br2 that you form from that termination, the propagation couldn't continue. Excuse me.
Did you ever want to do a bromination one that has like resonance?
I'm sorry, I couldn't hear you.
One of the allylic bromination ones that has like resonance. So,
Allylic bromination with resonance.
yeah.
Okay.
Yeah.
Okay. So allylic brominations are always performed using NBS. That's N-bromosuccinimide is our primary source of bromine. I'm just going to be lazy and draw NBS. I'm not going to draw the structure. I'm just going to use the acronym. Okay. So for allylic halogenations, allylic brominations, again, let's go back to initiation. First thing you want to do is you're going to take this NBS, and this NBS has a Br in it, all right? So again, the first thing that you want to do is you want to produce that bromine radical. And so basically, that's going to split that Br off the rest of your NBS structure. It's actually a nitrogen bromine bond. So you're left with an NBS radical, which we don't care about, and Br radical, which we do care about. Okay. All right, you've got that. Now you move on to propagation. All right, you have your hydrocarbon, and you have your Br radical. All right, which spot are we going to specifically target with our Br radical? I see several of you going like, use your words, people. What's that?
Third carbon.
From, yeah, this one, right? AKA the allylic carbon. Yeah, you're going to target an allylic hydrogen, right? So you're going to abstract an H radical. and make HBr. That's a waste product. We don't care about it. And more importantly, you're going to make your allyl radical. Now, there's a couple of different things that can happen with this allyl radical. What's the most direct, easy thing to do with it? I'll remember. What could this allyl radical interact with? Br2. Yes, exactly. Now, where the heck did the Br2 come from? Yeah, this is where that important termination is, right? So don't forget that. You have a very important termination step here that can happen between two Br radicals to produce this guy, which cycles back in over here. The Br radical can break off and attach itself to that allyl allyl carbon and give you product. And this one actually produces a new stereogenic center, so it's going to be a raceme. Okay. Does that make sense? Now, that's not the only thing that can happen. What else could happen with this allyl radical? Resonance. Yeah, this is where resonance comes in. Allyl radicals are stabilized by resonance, which means this pi bond can split, and these two electrons can sort of meet in the middle and make a new double bond, and this electron could stay over here. And so there's your other resonance structure, which could also interact with Br2 and give you a different product. So that's something you always want to account for. If you're doing an allylic bromination, make sure to account for the possibility of resonance. That is not something you have to do for radical addition to a double bond or just regular radical halogenation, just for allylic. Yeah. Any other questions?
There's one book that was cyclohexene with a methyl group on one, and then two carbon filters, a double bond methyl group.
All right, 1 second. Okay, so let's see, you had cyclohexane, and what else?
A methyl group. And goes 2 carbons down to the bottom one, and then a double bond.
Like that?
Reacted with MDS. And ask for all the possible products.
Okay. All right, this one, well, let's see. I'm going to skip ahead in this one, right? I'm going to skip past the initiation step. I'm going to go directly to this. All right. Now, this one's a little bit different than the last one, although you approach it the same way. All right, so you ask yourself, how is this Br radical going to interact with my hydrocarbon? What did it do last time? It attacked an allylic hydrogen, right? Well, what's the difference between this hydrocarbon and the one we had in the last problem? There's two allylic sites, and that will happen fairly commonly, right? Now, sometimes you'll only attack one of them, but sometimes you'll attack both of them, right? Again, look at the possibilities. You could abstract the hydrogen off that carbon, or you could abstract one off of that carbon. And those would be the respective radicals that you would make. All right, so you got the possibilities. Now you have to ask yourself, all right, is either one of these favored over the other one? Are they about the same in stability? What do you think? Well, what kind are they? What kind of radical do you have on the left? Secondary allylic, right? So the radical on the left is secondary allylic. What about the other one? Also secondary allylic. So guess what? You got to work off of both of them. Yeah. So one like this is a little bit messier. You have two distinctive secondary radicals. Equal instability, it means they're both going to form. So that means for each one of these radicals, you have to do the direct attack of BR and then draw the resonance structure. Yeah. So fast forwarding, working off the left radical. We have that. And that. Working off of this radical. We have that. And that. And then, of course, racemates, stereoisomers, etc. I think each one of these would exist as a racemate, so you'd have like 8 different stereoisomers. So yeah, they can get a little complicated, but you would have to work off of both of them. Here's a question for you. What if it was that? Well, let's look at it. I want to erase some of this so it's not in the way. Again, look at the possibilities. You could take an H off of that allyl position, or you could take an H off of this allyl position. Is either one of those favored over the other one? I see some nodding. Which one? The left one? Why? Tertiary allyl over secondary. So in this case, you would only work off of that one. Very good. Congratulations, you have done a fantastic job of stalling me so that I could not teach you new material today. Mission accomplished. Everybody's nodding, like, nice. Okay. In all seriousness, hopefully you guys got your questions about the exam material answered. I will be around this morning with, I'm in a Zoom meeting from 11 to 11:30, but otherwise I'm available if you guys need to come by and ask questions. All right, cool. See y'all later.